this video, we're going to derive an expression for the density of a perfectly cylindrical wooden log of radius r floating in water on its side that extends a maximum distance of h above the water level. Here's a diagram to better understand the problem. H is the distance of the log that is above the water level, and this horizontal line is the height that the water reaches. R is the radius of the log, and L is the length of the log. So both the velocity and acceleration of the log are equal to 0. And here are some things that we need to keep in mind. Density equals mass over volume. The volume equals area times the length, and the area of a circle is pi r squared. The density of water is 1,000 kilograms per meter cubed, and weight equals mass times gravity, and the Pythagorean theorem is a squared plus b squared equals c squared. So gravity and buoyant force are the two forces acting on the log. So the buoyant force is the mass of the water times gravity, and this is equal to the mass of the log times gravity. So we have m sub w times g equals m sub l times g as well, which is gravity. And now in this equation, the g's cancel out, gravity cancels out, and we end up getting the mass of the water is equal to the mass of the log, or m sub w equals m sub l. And replacing these masses with the rearranged density equation, mass equals rho times volume, we get rho sub w, the density of water, times the cross-sectional area of the water on the log, which will be represented as 2/3 of the log, which is a semicircle, times the length of the log, L, and this equals rho sub L, which is the density of the log, times the area of the circle, which is pi r squared, and we'll also be multiplying this by the length. So the lengths cancel out on both sides, and we're left with the density of water times the cross-sectional area of the water on the log equals the density of the log times the area of the log space. We're trying to find the cross-sectional area of the water on the log, so we're going to create another equation for it. We have the cross-sectional area of the water on the log equals the area of the circle minus the top part of the log that is untouched by the water. So these are going to be figures to visualize it better. So we have essentially our 2/3 of the log, which is a semicircle, equal to the circle, minus 1/3 of the log, which is that untouched part of the log that the water doesn't reach. And if we extend the radius line to the other side symmetrically, it makes a triangle, including the log that is untouched by the water on top. So I'm going to draw that right here. And so we can conclude that the top part is equal to that figure minus this figure minus the triangle that was made by the radii. So drawing in another radius in between the existing radii and the height of the water, we get the height of the triangle that we just drew. And this is denoted as r minus h, and that's the height of the triangle. And now we need the area of the triangle, and we also have two smallest triangles whose bases are unknown. And the bases are going to be denoted as x instead of b, since we have yet to define it. So now we have two x's, and both of them have an angle of theta, which are down here. So I'll redraw the triangle and the semicircle figure right here, which is the cross-sectional area and the triangle, and that's going to be equal to 2 theta over 2 pi. And this is all multiplied by pi r squared. And the 2 pi are radians, and it's multiplied by the area of the entire circle. So the 2's will cancel out, and the pi's will cancel out, so we get our figure, and it's equal to r squared theta. And we don't know theta yet, so we're going to write an equation for it, and we get theta is equal to inverse cosine of r minus h over r. Using SOHCAHTOA, because our triangles we made are right triangles, r minus h is the adjacent and r is the hypotenuse of our triangle. Plugging in that to our equation of the triangle and semicircle figure, we get that that diagram is equal to r squared times the inverse cosine of r minus h over r. For this equation, we now need to find the area of the triangle. So we'll end up subtracting the area of the triangle from the diagram of the semicircle and triangle to get the part of the log that is untouched by the water. So 1/2 base times height is the area of the triangle, but remember that we denote the base of the triangle as x. So we have triangle is equal to 1/2 times r minus h, and r minus h is the height of the triangle, not h. Solving for x, we use the Pythagorean theorem, since we're dealing with the right triangle, so we get x squared plus r minus h squared, and this is equal to r squared. Rearranging this equation, we get x is equal to the square root of r squared minus r minus h squared. Simplifying and factoring, we get x equals the square root of negative 2rh minus h squared. Plugging this new equation into the area of the triangle equation, we get that the triangle is equal to 1/2 times the square root of negative 2rh minus h squared, and all this is going to be multiplied by 2, since we have two triangles and we want the area of the entire triangle, and this is also going to be multiplied by r minus h because that's the height. It's 1/2 base times height, and this base is that x. So the 1/2 and the 2 cancel out, and now we're left with the triangle is equal to the square root of negative 2rh minus h squared, and multiplied by r minus h. So now the top part of the log that is untouched by the water is equal to r squared inverse cosine of r minus h over r. And we have this minus the square root of negative 2rh minus h squared times r minus h. Redrawing the figure equation of the semicircle, which is the cross-sectional area of the water, is equal to the entire circle minus the smaller cross-sectional area of the untouched log. Plugging in what we know, we drop down the first semicircle, and I'll redraw that, and we have that it's equal to pi r squared minus r squared inverse cosine of r minus h over r minus the square root of negative 2rh minus h squared, and then this is multiplied by r minus h. Now we can rearrange the figure equation to get the density of the log. So the density of the log, which is known as rho sub L, is equal to the density of the water times the cross-sectional area of the water on the log over the area of the circle. So the equation is rho sub L equals rho sub W times the semicircle over pi r squared. Remember that the density of water is 1,000 kilograms per meter cubed, so we end up getting 1,000 times pi r squared minus r squared inverse cosine of r minus h over r minus the square root of negative 2rh minus h squared times r minus h, and all of this is divided by pi r squared. And this is how you'd find the density of a perfectly cylindrical wooden log that's floating in the water. I'll just clean this up a little bit. And there you go. Thank you.